Hello students, welcome to section 14-5. Today we're going to be talking about segment measures. The following theorems can be used to find the measure of special segments in a circle. First, if two chords of a circle intersect, then the products of the measures of the segments of the chords are equal. Let's take a look at a depiction of this to help frame our understanding as we continue. So here's a circle where, let's say we have our two chords. Again, two chords of a circle intersect, let's say as such. We'll draw a chord here and a chord there. I do want to make sure that as we kind of generalize this first theorem, that we're clear about defining, the first chord that I drew in such a way where we can break it up with, this being the intersection point inside the circle, but this segment A and this segment B are comprised, or they are comprising, I should say, that full chord. So segment A and segment B together give you that first chord, while let's say segment C and D combined give you that second chord. So again, if two chords of a circle intersect, then the products of the measures of the segments of the chords are equal. So the product of the measures would look something like this. We would say A times B simply is equal to C times D. Now, in various problems that we're going to take a look at, we will be given likely 3 out of the 4 values, and you're going to be able to solve for the fourth. In this particular context, generally speaking, it's a matter of just once you multiply, you'll be dividing by one of the values. It's a very nice theorem to start this process of segment measures. The second theorem: if two secant segments are drawn to a circle from an exterior point, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. Give ourselves another depiction here to kind of generalize. And somewhat like we did on the prior theorem and problems prior to this in the prior sections, I'm going to go ahead and frame this where, unlike the last problem where we had chords, this is going to have secants. So here's how this is going to take shape. Here's one secant. I'm going to draw a point outside as such in which the other secant happens to intersect. Okay, so we have two secant segments, again, intersecting outside of the circle at this exterior point. Again, the product of the measures of one secant segment and its external secant segment. So a full secant segment, and this time I'll use, let's say, points on the circle here, here, and then here, and here. To help justify things, I'll use point A and B, and then C and D. Let's call point P the exterior point that both secants intersect at. As far as the the product of the measures of one secant segment and its external secant segments, well, respectively speaking, each secant has its own external secant segment. So this on its own is technically an external secant segment. Clean that up a little bit. Sorry, so external secant segment, BP. Well, this is also an external secant segment. And that, of course, well, is DP. Okay. We do have two secants still to decipher and depict in our equation here in a moment. So let's go ahead and consider the very first secant segment where AP can be utilized appropriately in context. So again, we're talking about, I'll highlight the product of the measures of one secant segment and its external secant segment. So that would be quite literally AP times the external secant segment BP, and that will be equal to the product of the other secant segment and its respective external secant segment. In other words, CP times dP. So similar to what we saw in the last theorem, you will be given likely on pretty much every problem 3 out of the 4 values of secants and or external secant segments, and then you'll simply multiply and then divide to finish the process. Now the last theorem is actually going to be more specifically discussed in the example just below. I'm going to read through and then we'll talk about the example. If a tangent segment, and a secant segment are drawn to a circle from an exterior point, then the square of the measure of the tangent segment is equal to the product of the measures of the secant segment and its external secant segment. So there's a lot of similar language here, except now we're also deciphering in our equation utilizing a tangent. I'll decipher that and utilize that here in a moment. In the example, you see, find the value of x to the nearest tenth. AB, that is very specifically the tangent, as I've already noted, and that is provided, like I said, 18, and as you see, 18 technically. And that's equal to the product. Well, the square will be applied as well in context, so I'll circle that. So it's the square of that tangent, technically. And then that's equal to the product of the measures of the secant segment and its external secant segment. So I'm going to designate our secant, not external secant segment, but secant as simply the entire value x plus 15. We don't know x, but that's going to be a part of our formula here in a moment. And the last bit here is the external secant segment, which would be this particular value of 15, and I'll designate it off separately again. The external secant segment, and that's kind of specifically 15, but more generally to relate back to the last theorem, let's say simply CB. Okay. Let's jump back to the application. Okay, so AB squared, again, the tangent squared essentially. So tangent squared is equal to BD, which again is that entire secant of x plus 15, which you'll see here in a moment, times BC, or CB, same thing. So you'll see here in the next step, you can substitute, of course, 18, which is what we're given for AB, so 18 quantity squared equals, again, like I said earlier, x plus 15 plus x, same thing, times 15, which you're also given. The math is straightforward from here. I would argue just simply square 18, 324. You can and should distribute the 15, and in doing so, you'll end up with, well, 225, because 15 squared, 15 times 15 is that. 15 times x, of course, 15x. Subtract 25, so 99 equals 15x, and divide. Your final answer then ends up being 6.6. So that's the third theorem in application. Now these theorems are a bit more involved, I would argue, than some of the other ones we've looked at prior to this. But if you take your time and label things, it should hopefully relate very nicely to the kind of more generalized depictions that I've noted above. Let's move on. So find the value of x to the nearest tenth. Assume segments that appear to be tangent are tangent. So if we look at number 1, this would very obviously, I would argue, relate to the first theorem as a chord-chord relationship. The chord-chord relationship, again, as we saw back on theorem 1, remember I had indicated it was simply A times B equals C times D. We're essentially just taking the product of the segments, kind of, again, giving you that combined chord. So 6 times x equals 3 times 8. And of course, that's as easy as 6x equals 24. Therefore, divide by 6, and boom, x equals 4. Number 2. So in this depiction, you can see here that we're provided a secant and another secant that intersect outside the circle at one particular value or point, I should say. The values of which are also provided, which is nice, which if you kind of look at, again, the three theorems we started, this nicely relates back to the second theorem. The nice part that we can kind of add to the picture, though, noting that we've got congruent segments with this marking here and this marking here giving us 8 as well. That's going to give us the ability to do the math, again, such that we're multiplying the secant times its external secant segment and set it equal to, well, the other secant and secant segment multiplier, so to speak, as we showed in the example above. So let's take a look. So we're going to go ahead and simply, let's do this little bit of extra math. Add these two to get 16. Add these two to get 2x plus 6. So again, as the theorem suggests, we'll take 16 times 8. I'm going to circle the external secant segments so you can kind of more easily differentiate. So there's one and there's the other. So again, back to the context of the formula application or theorem application, will be 8 times 8, or excuse me, 8 plus 8 first, which is 16, that times 8. And that's equal to parentheses 2x plus 6 times 6. Okay, so if we do this math, multiply 16 times 8, and that then lends itself to then what, 128, and that could be set equal then to what? If we distribute the 6, we'll be left with 12x plus 36. Let's do some additional math, of course. If we subtract 36 from both sides, that value 92 equals 12x divided by 12, and we'll end up with 7.6 repeating, or 7 point, to the nearest tenth, we'll say 7.7. That is the value of x. If you were asked to find, let's say 2x inside the circle, just that alone, you could simply multiply 2 times what we just got and get your kind of more specific chord value, which again, as hopefully we kind of can bring back from other sections, a chord is inside the circle because its endpoints are on the circle. Just to kind of keep that in mind for the future. Let's do one more problem in application of, let's say, the third theorem, which we haven't yet done so in this particular little 9-problem section of questions. The one in particular that I think would be nice to kind of take a look at would be number 7. So if we take a look, this would be a tangent, and then again a secant, where it has an external secant segment of 5x, but the secant itself we can highlight as such. The secant is simply 5x plus 9. According to the theorem up above again, it is a matter of squaring the tangent. So we do know the tangent is 13, so that'll be 13 squared. And that will be equal to the product of the secant and the external secant segment. So let's multiply, let's just put the external secant segment first and then the secant. We'll continue by squaring 13. 169. That equals, if we multiply, we got 25x squared, and then plus 45x. So now when you set this quadratic equal to 0 by subtracting 160 from both sides, a little bit of extra analysis, particularly the quadratic formula, which I will describe in another audio version of this or continuation of this, you'll end up with 1.851 for x, or rounded to 1.9.